Okay, welcome back everyone. In this video I'm going to give you a quick example of how to solve problems using Faraday's law. And so this is number 8 from chapter 29, and we're given a circular steel ring, so we're going to look at it edge on, which has a radius of 0.75 meters, and we have a magnetic field that changes as a function of time, and it's making a 60-degree angle with the ring itself. So what we have here is a magnetic field that's basically 1.4 Teslas e to the negative 0.057 seconds to the minus 1 t. And so if we want to, in part A, find the EMF as a function of time, we're going to have to use Faraday's law, which says that the electromotive force is equal to negative d flux dt. And just as a reminder, d flux dt actually has two pieces to it, because flux is B dot A. We can have a change in flux two different ways. We can have a change in flux because the field is changing or because the area is changing. And in this case, the area is constant and the field is changing. So it's often a good idea to write this out, that negative d flux dt is actually negative b dA dt plus negative a dB dt. And as we said a moment ago, the area isn't changing, so that first term is 0. So we just need to calculate negative a dB dt, but let's not forget we also have a cosine of the angle between the normal and the field, so cosine of 30 degrees. So we'll plop that in there. That's going to be a root 3 over 2, and we get an EMF of negative a, which is negative pi times r squared, and dB is going to be our original 1.4 t e to the negative 0.057 times time, and then that's going to be times our derivative, so it's negative 0.057, and the two negatives are going to cancel out. So this means that the EMF as a function of time is going to be 0.122 Tesla meters squared per second e to the negative 0.057 t. And there's an over seconds if you wish. Okay, and so this is basically our answer to part A. This is the electromotive force as a function of time. Now in part B, we want to find the time when this EMF is equal to 1/10 of the original. And so the original is going to be this, that's E naught. And so really what I'm trying to solve for is that the final value is 1/10, and I have the initial, and I'm going to solve this equation for time. So I'm going to multiply each side by 10 if you want, raise or take the natural log of each side. That'll get rid of my e. And anyways, a little bit of math later, we get a time of about 40.4 seconds. Okay, now in the last part, part C, we want to find the direction of the induced current in the loop as viewed from above the loop. Okay, so this is where it gets a little bit tricky. So here's above the loop, okay? This is kind of a top view. And so that means that the magnetic field is coming out of the loop. Okay? But what we want to do is we want to think about what is happening to the field. Well, the magnetic field is decreasing. Okay? So B of t is decreasing, so dB dt is some negative value. And what we could say is that the change in the field is into the page. That's the way that the field is changing. And Faraday's law says that the induced field will always oppose any change. And this is the part that's so difficult to understand and to put into practice. The induced field will always oppose any change in the magnetic field. Okay, so what we can do is we can think about this kind of from a side view, okay? And if the field is, let's say it's coming straight out, we know it's not, but this is B initial, and what's happening to the field is that it's becoming less. In other words, this is the change in the field, is into the page, which means that the induced field must come out of the page in order to cancel out the change. So another way we can say this is that B induced will be opposite the change in the field. Now, to be fair, we should be talking about the flux, but in this case, because the flux is only determined by the value of the field, then I can simplify it. And if I draw this in my diagram, well, I know that the induced flux, or the induced field, must be coming out of the page in order to oppose the change in the flux or field, which is into the page. And because of this, with the right-hand rule, I'm going to get a current which is counterclockwise current. Okay, so the induced current is counterclockwise. Okay, remember that that voltage, that induced voltage E, is current times resistance. So if you want just the current, you're going to have to divide E by R to get the current. Okay, but in any case, let me get rid of my chicken scratch here. The current is going to be counterclockwise. So there's one example of how to deal with Faraday's law when you have a changing magnetic field. In the next example, we'll talk a little bit more about how this works with Lenz's law.